Welcome protein coders, let's build some coding muscles. Today we're gonna see shortest path in DAGs or directed acyclic graphs. Let's come to our graph. We have a cyclic directed graph in which we have edge weights. Okay, and we have to find out shortest distance of each node from our starting node, or let's say node 0 in this example. Okay, now let's try to do it using TFS. Let's see. Let's traverse to node number 2 from 0. Okay, and perform our DFS. So then 2 will be at distance 5, 4 will be at distance 11, right? 5 will be at distance 13, 6 will be at distance 15, and 7 will be at distance 16. Okay, but if you look at the node number 4, it is not the shortest distance from node 0. Why? Because if we take another DFS, let's take another DFS, 1 will be at distance 1, 3 will be at distance 4. Now we will reach 4 at distance 5, right? So we'll update this. Then we will move to node number 5. So again we can reach it in shorter distance, right? Similar to node 7 will be at 10 and 6 will be at 9. So from here we get an observation that if we perform DFS, we have to perform multiple DFS, right? And we have to update the node distance of nodes again and again, and time complexity will increase. That's why we will use BFS. Let's see. So node 0 will be at distance 0 and 2 and 1 will be at distance 5 and 1. Okay. Now in the next traversal, from 2 we will move to 4 and from 1 we will move to 3, right? So we'll update the distances. So 4 will be at 11 and 3 will be at 4. Okay. But if you observe carefully, again we got our shortest distance as 11 at 4, which is false, right? So BFS is also giving us wrong answer. Why? Because this node 4 is the problem node. But if you observe carefully, this shortest distance as 4 is dependent upon 2 and 3, right? We can write it as minimum of distance of reaching at 2 plus the edge weight between 2 and 4, comma, distance of reaching at 3 plus edge weight between 3 and 4. So if you see, 4 is dependent on node number 2 and 3, right? Similarly, node 3 is dependent on node 1. And shortest distance at 2 is dependent on 0, as in case of node number 1. So if you see carefully, the shortest distance which we are calculating, for 4 it's dependent on 2 and 3, for 2 and 3 they are dependent on node number 0 and 1 respectively, and for 1 it's dependent on 0, for 5 it's dependent on 4, for 6 and 7 it's dependent on 5. So if you observe carefully, what is this? We have studied this in our previous lectures, right? It is nothing but a topological sort. So if you observe, if we process our nodes, right, in a topological sorted order, we will get the correct answer. You got the point, right? Why we get the correct answer? Because if we go in topological sorted order, right, we will get the shortest distance at every node. Okay, so let's start doing it. At 0 we will mark it as 0, right? Now we'll move to 1. So distance to reach the parent of 1 plus edge weight, right? It will be 1. Then similarly for 2 it will be 5. Then in a toposort we will process 3. So at 3, minimum of distance of 1 plus 3. Okay. Now when we move at 4, you will see we have 2 nodes, right? So now this minimum will comes into the role. So this time minimum of 5, 11, right? We have 2 options. So we will choose the smallest one, shortest one. So we'll get the correct shortest distance for 4. Then we will go to 5, it will be 7, and for 6 and 7, we will similarly get 9 and 11. Oh, sorry, 10. So here you can see, right? We will traverse and process our nodes in topological sorted order, and in one pass we will get the correct shortest distance. Okay, now let's see the code. First thing first, let's get a stack, a vector visited, and we'll call a toposort function. We studied this in our previous lecture. You can go back and watch that. Okay, so from here we got the toposort in a stack. Now let's create our distance vector and initialize the distance of 0 is equals to 0. Now while stack is not empty, be very careful, we are using stack here, right? Our Toposort. We'll get the node, we will pop it out, we will traverse for its neighbors, and if the distance of neighboring node, okay, is greater than the distance of parent node plus the edge weight, we will simply assign it the distance of node plus edge weight, and that's it. At the end we will return our distance vector. Okay, now let's revise what we have studied. Okay, so we saw, like in DAGs, if we try to find shortest paths using DFS, it will be very heavy time complexity. Okay, and BFS is also not giving us the correct answer. So we observed that in this diagram the node number 4 is the problem, right? And for 4 we got an observation, right? At 4 we can process it using the distance, shortest distance at 2 and 3 plus their edge weights, right? And we got this relation, and using this relation, right, we observe that it's nothing but Toposort, right? We can use Toposort here to process the nodes, and when we process the nodes in a Toposort order, we got the answer in one pass. And we saw the code for it, we got the Toposort first, and then we just process the nodes according to our Toposort, and whenever we found that the distance at the neighboring node is greater than the distance at the node plus the edge weight, we will update the distance of neighboring node, and at the end we will return the distance. So that's it from my side, guys. Thank you for listening. If you have any questions, please mention them in comment box. You will find the problem and solution link into the description box. If you don't understand, don't subscribe, but if you do, please show some support. Keep smiling, keep coding, keep practicing. Thank you.